Good morning, everyone. Welcome to Guru Brahma classes for JEE and NEET. We are in the chapter Chemical Equilibrium, and in this session, we are going to discuss about equilibrium constant. Okay, what are the types of equilibrium constants? Right? Let's start. So here we are seeing law of mass action. What is that? Law of mass action. So it was proposed by Hulberg and Waage. So what is this law and what information does this law gives us? This law gives a relation between what and what? Rate of a chemical reaction and concentration of a reactants. Rate. Okay, rate of a chemical reaction and concentration of reactants. Already we have discussed that rate of a reaction is represented as R. What is that? Rate of a reaction is rate of a reaction. Rate of a reaction is represented by R. Okay. Rate of reaction with respect to reactants. Let us take that reactants gives rise to products. So rate with respect to reactants is given by change in the concentration of reactant by change in the time, or rate with respect to products is given by change in the concentration of product by change in time. So this is already we have discussed. Now law of mass action we are discussing. What is law of mass action? According to law of mass action, according to law of mass action, for example, let us take A moles of A is reacting with B moles of B to give you C moles of C and D moles of D. What are small a, b, c, d? These are the stoichiometric coefficients in a balanced equation. You know balanced equation? Okay. To prove the law of conservation of mass, generally we balance the chemical equation. In that chemical equation, the small a, small b, small d, small c are stoichiometric coefficients, and capital A, capital B, capital C, capital D are capital A and B are reactants, capital C and D are products. So this is an irreversible reaction. Irreversible reaction. For this irreversible reaction, what does law of mass action says? Is they say that or the law says that rate is proportional to concentration of reactants, product of the concentration of the reactants, and this concentration of the reactants powers are written as the number of moles in the stoichiometric equation. So in the stoichiometric equation or balanced equation, how many number of moles of A are there? Small a. So that small a is written as the power to this concentration of A, and small b is written as the power to the concentration of B. Okay, so this is what law of mass action says. Law of mass action says that rate of a reaction is directly proportional to the product of the concentration of reactants powers raised as its number of moles in the balanced equation. Okay, this is what law of mass action says. See, the rate of a chemical reaction at a given temperature is directly proportional to the product of the active masses. Active mass is nothing but concentration. Okay, active mass is that concentration of A and B present at that particular instant. The active mass, the mass of that substance which is active, which can react, which can participate in the reaction. Active mass here is nothing but what? A concentration. That is the reason why directly we have written it as a square bracket. Square bracket represents that the concentration. So active mass of the reactants at that instant, at that particular time, where the reactants are reacting, how much concentration of A is present, how much concentration of B is present. So rate is depending upon those concentrations of A and B present at the time of the reaction. So I can write here concentration of A and B we can say that these are the concentrations of A and B present at the time of reaction. At the time of reaction. At the time of reaction, at that particular instant, the rate of the reaction is directly proportional to concentration of A and product of the concentration of A and concentration of B, powers raised as its number of moles in stoichiometric equation. Okay. So this concentration is also called as active masses. The mass of that reactant active at that particular time to react. So this law is applicable to all reactions occurring in gas phase or in liquid phase. Active mass is also called as what? Molar concentration and indicated by square brackets. Active mass is nothing but is equal to molar concentration square bracket, and concentration is given by number of moles per volume expressed in liters, which is nothing but molarity. What is that? Molarity is number of moles by volume expressed in liters. This is mathematical representation of molarity. Active mass of a gas is its partial pressure. If the substance is gas, for example, nitrogen gas. Okay. If you are speaking about active mass, its pressure, partial pressure. Active mass is nothing but what? Partial pressure. You can also take concentration, but if you when it is in the gas, you can take concentration of nitrogen as active mass, or you can also consider partial pressure as active mass. So pressure can be taken as active mass, partial pressure can be taken as active mass only for the case of gases. Only in the case of gases it is taken. Okay, active mass, this point is to be remembered. Active mass of solid and pure liquid is taken as unity. Unity is nothing but 1. Active mass of a solid and pure liquid. So for example, iodine solid, its active mass or concentration is how much? 1. You take bromine liquid, active mass is 1. You take whatever metals in solid, okay, its active mass is equal to 1. So during a reaction, their concentration does not change much. That is the reason why their active masses are taken as 1, considered as 1. So here is a question given. 8.5 grams of ammonia are dissolved to form 4 liters aqueous solution. That means there is water here. What is that? Water. In this water, what you have pumped? 8.5 grams of ammonia you have passed. Then let us consider this is closed. Okay. So water volume after passing 8.5 grams of ammonia, volume of solution is equal to, okay, 4 liters. Then calculate active mass. Active mass here if you calculate active mass is nothing but the concentration, that nothing but the molarity, number of moles by volume expressed in liters. So number of moles of ammonia is equal to given mass by molar mass, okay, molecular weight we can also say. How much? 8.5 grams ammonia, NH3, nitrogen 14, 3 hydrogen 3, how much? 17 grams. Okay, then what do you get? 1 by 2. So active mass, number of moles we have calculated as 1 by 2 by how much volume? Volume of the solution in liters, 4 liters. So 4 liters, that is equal to 1 by 8 moles per liter. Right? So that's the answer. Understood? Next, coming to equilibrium constant with respect to molar concentrations. When reactants and products are expressed in concentration, their molar concentrations, then such equilibrium constant is called as concentration equilibrium constant or equilibrium constant with respect to molar concentrations. We call it as Kc. C represents concentration. C represents a concentration. Right? So let us see here. A moles of A react with B moles of B, giving rise to C moles of C plus D moles of D. So you have both forward arrow and a backward arrow that represents that the reaction is a reversible reaction. Only for reversible reaction there is possibility for the attainment of equilibrium. So when the rate of forward reaction is equal to rate of backward reaction, automatically it attains equilibrium. Right? So let us say that this reaction is in equilibrium. Okay. Then for forward reaction, apply rate law or law of mass action. If you apply that rate of forward reaction, rate F I am writing, rate of forward reaction is equal directly proportional to, right, concentration of product of the concentration of product reactants. Okay, concentration of A power A and concentration of B power B. So RF is equal to, if I remove the proportionality constant, I can write K, proportionality constant K or rate constant K. I can say that it has a rate constant. As it is forward reaction, I am writing F, concentration of A power A, B power B. Backward reaction. I am speaking about the backward reaction. Why I am speaking about backward reaction? But for a reversible reaction, we have backward reaction also. And in the backward reaction, which becomes reactants? C and D becomes reactants. For backward reaction, what happens? C and D becomes reactants. A and B becomes products. As C and D becomes reactants, and we can also apply rate law or law of mass action to this. If you apply that, rate of backward reaction is equal to Kb into concentration of C power C and concentration of D power D, we get the same. And we know that at equilibrium, we have studied that rate of forward reaction is equal to rate of backward. Rate as I bet. Rate of forward reaction is equal to Kf into concentration of right, A power A into B power B is equal to Kb into concentration of C power C and D power D. Okay. If I write here Kf by Kb, Kf by Kb is equal to C power C into D power D by, right, A power A into B power B. Okay, Kf by Kb is ratio of rate constant for forward reaction by rate constant for backward reaction. What is Kf? Rate constant for forward reaction. And what is Kb? Rate constant for backward reaction. So this is called as equilibrium constant. What is equilibrium constant? It is the ratio of rate constant for forward reaction to rate constant for backward reaction. Kf by Kp. Okay. As the products and reactants are represented in concentrations, this K equilibrium here it is called as what? Kc. Why we are mentioning it as Kc? Because the reactants and products are represented in concentration terms. Reactants and products are represented in concentration terms. That is the reason why this equilibrium constant is also called as what? Kc. So what did we get here? K equilibrium is equal to product of the concentration of the products. You can see here in the mathematical representation or in this representation, product of the concentration of the products at equilibrium. See what are C, D, A and B? This A and B are concentration of A and B at equilibrium. This C, D, these are what? Concentration of C and D at what? Equilibrium state. At equilibrium state, right? See, at equilibrium, here also at equilibrium. This representation is known as equilibrium law or law of chemical equilibrium. Let us consider a reversible reaction. Whatever the reaction which we have seen here, that is what is written here. What is Kf? Rate constant for forward reaction, and what is Kb? Rate constant for backward reaction. And concentration A, B, C, D concentrations are equilibrium concentrations. That means concentrations at the equilibrium state. At what state? Equilibrium state, right? So now what we have written? K equilibrium. Kc we have written that concentration of C power C and concentration of D power D, okay, by concentration of A power A and concentration of B power B. So everything is concentration. What is that? Concentration. Square bracket means concentration. So then I can write C plus D minus A plus B, right? A plus B. So units, if I write units is equal to units of whom Kc is equal to, what is this square bracket expression represents that it is moles per liter, moles per liter, moles per liter, C plus D. Okay, so C plus D minus A plus B, A plus B. So in another words, I can write moles per liter delta N, where delta N is equal to number of moles. C plus D is total number of moles of gaseous products. What you can write? Number of moles of gaseous products minus number of moles of gaseous reactants. Only which are in gaseous state, those number of moles we need to calculate. We need to take. So I can write delta N is equal to Np minus Nr. Okay. Np minus Nr. Say moles per liter delta N. Moles per liter delta N, where delta N is equal to Np minus Nr. Number of moles of gaseous products minus number of moles of gaseous reactants. So let us see, there is a question here. What is the equilibrium constant for the reaction, given reaction? Okay, Kc is given. Kc is equal to 10 liter square per mole square. The rate constant for backward reaction is 2.8 per second. And what is the rate constant for forward reaction? Kf is asked. Okay. We know that Kc, now only we have studied that Kf by Kb. Kf is equal to, backward reaction is given and forward reaction is asked. So Kf will be equal to what? Kc into Kb. Kc given 10 into, right, 2.8. Then what do you get? 10 into 2.8, 28. Okay, per second. So rate constant for backward reaction is given 2.8. What is asked? Rate constant for forward reaction. So rate constant for forward reaction is equal to Kc into Kb. Kc into Kb we have calculated, right? Next. Question number 3. For the cyclic trimerization of ethylene to give 1 mole of benzene, actually cyclic trimerization means 3 moles of C2H2 when it is passed through red hot iron tube or copper tube, what you get? C6H6. For this reaction, so he is mentioning that it is happening in both the directions. For this reaction, they gave it as Kc. Kc is equal to 4 liter square per mole square. If the equilibrium concentration of benzene is 0.5, calculate the equilibrium concentration of acetylene. For this reaction, if you write Kc, then what you write? Concentration of C6H6 by concentration of C2H2 power 3, because 3 is there in the stoichiometric equation. Okay. So then what is asked? Calculate the equilibrium concentration of acetylene they are asking. So equilibrium concentration of acetylene. C2H2 power 3 is equal to Kc into concentration of C6H6, right? Concentration of C6H. Kc is given how much? Kc given how much? 4 into equilibrium concentration of benzene given 0.5. Okay. So 4 into 0.5. Oh, we don't get this right. What do we get? C2H2 concentration is equal to C6H6 concentration by Kc. C6H6 concentration how much given? 0.5 moles per liter. 0.5 moles per liter by Kc how much given? 4. Okay. Then you are asked only C2H2 concentration. So what do you get? 0.5 by 4 whole power 1 by 3. Right? That is how we get the answer. Kc given 4, whereas benzene given 0.5. Right? Then the concentration, what do you get? Right? Moles per liter. Next, let us. Equilibrium constant with respect to partial pressure. Before we have discussed that equilibrium constant Kc. Kc means equilibrium constant with respect to concentrations, molar concentrations. But here what we are speaking, equilibrium constant with respect to partial pressures. Partial pressures. Okay. Whenever we are seeing this partial pressure, we have to remember that either reactant or product must be in their gaseous state. They must be present in gaseous state. Then only we can take those partial pressures into the context. So what is meant by partial pressure? Already we have discussed. Let us once again know that if there is a particular gas, like for example, let us take carbon dioxide. So when there is only one gas in a container, we say that if this is exerting pressure, then we say that pressure of carbon dioxide. Okay, what we say? Pressure of carbon dioxide. But in a container, if there are more than one gases, if there is only one gas, then only that gas will exert pressure. Only that gas exerts some pressure. But if there are more than one gas, like carbon dioxide and helium, these two are not reacting with each other. Carbon dioxide will exert pressure, as well as helium gas is also exerting pressure. Then what is the pressure exerted by carbon dioxide? Called as partial pressure of, what is that? Partial pressure of carbon dioxide. Why we are using partial pressure? When do we use partial pressure? Word called as partial pressure. We use the word partial pressure when there are a mixture of gases and each gas is exerting pressure. Carbon dioxide exerts pressure and helium gas exerts pressure. The pressure exerted by carbon dioxide is called as partial pressure of carbon dioxide, and pressure exerted by helium in this mixture is called as what? Partial pressure of helium. Partial pressure of helium. So when do we use the word called as partial pressure? We use the word partial pressure when there is a mixture of gases and they are not reacting, and each gas is exerting pressure, then we say, or we use the word called as partial pressure. We have studied a law called as Dalton's law. Dalton's law of partial pressure. In the chapter called as gaseous state, we have studied this Dalton's law of partial pressure. Partial pressure. Okay. So in this Dalton's law of partial pressure, we have studied that in a mixture of non-reacting gases, the partial pressure is equal to mole fraction into total pressure. PI means partial pressure of a particular gas, X is mole fraction, PT is total pressure. So this formula will be useful for solving problems. We need to remember this. So partial pressure word is used for a mixture of non-reacting gases. Partial pressure is used to find when there are a mixture of gases. Right? So let us consider a reversible reaction. Okay. A moles of A plus B moles of B gives C moles of C and D moles of D. Okay. So A moles of A plus B moles of B gives you C moles of C plus D moles of D. All these are what in gaseous state. Let us consider all of these in gaseous state. Apply law of mass action. Law of mass action, if you apply, what is that? Rate of forward reaction. Rate of forward reaction is equal to Kf into, as these are gases, before we have spoken that they can also be represented in the terms of partial pressure. Partial pressure of A power A into partial pressure of B power B. Because these two are reactants. This is for whom? For forward reaction. Okay. For backward reaction, let us take RB is equal to KB into partial pressure of C power C into partial pressure of D power D. This can be because in the same container all those four gases are present. See, here the reaction is happening in this container, right? When this reaction is happening in this container, what are present in this container? A is present, B is present, C is present, D is present. Reactants and products are present, and they are present in gaseous state. That means, and they are not reacting. Okay, they are reacting, but they are present. Their concentrations, their pressures are constant. So A is exerting pressure, B is exerting pressure, C exerting pressure, D exerting pressure. So in a mixture of gases, when they are present as a mixture, then we use the word called as what? Partial pressures. Okay. So this is for whom? Backward reaction. Which reaction? Backward reaction. And we know that at equilibrium, RF is equal to rate of forward reaction is equal to rate of backward reaction. Then I can write Kf into partial pressure of A power A into partial pressure of B power B is equal to Kb into partial pressure of C power C into partial pressure of D power D. Okay. Then I can write Kf by Kb, which is equal to partial pressure of C power C into partial pressure of D power D by partial pressure of A power A into partial pressure of B power B. Okay, which is called as K. Now we are mentioning it as K equilibrium. This K equilibrium can be mentioned as Kp. Why? Because we have represented these reactants and products in their partial pressures. That's the reason why we are mentioning this equilibrium as Kp. Okay. So pressures, if you go with the units of Kp, if you write, all are pressures. Pressure, if I mention it as atmosphere, C plus D minus A plus B. Before already we have discussed that it is delta N, where delta N is equal to number of moles of gaseous products minus number of moles of gaseous reactants. Okay, that is all about Kp. So Kp representation. So these are equilibrium partial pressures. So A, B, C, D, PA, PB, PC, PD, we have written now. All these are pressures at the equilibrium state. At equilibrium state of A, B, C and D. So units already we have written. Kp is equal to atmosphere power delta N. Right? Now you are given some reactions. CaCO3. Let us write first reaction. CaCO3 gives rise to CaO plus CO2. This is solid. This is also solid. This is a gas. Right? Then what will you write Kc? What will you write Kc? So Kc is equal to concentration of the products, CaO concentration into CO2 concentration by CaCO3 concentration. Okay, already we have mentioned that concentration of solid is 1 unit. So 1 into concentration of CO2 by, this is also 1. So simply I can write it as concentration of CO2. How to write Kc and Kp? We are speaking. How to write Kc and Kp? If I write Kp and CaCO3 and CaO both are solids, so I cannot take those partial pressures. I can take only partial pressure of CO2. So partial pressure of CO. This is how I write Kp and Kc for this equilibrium reaction. Let us see the next one. What is given? H2 plus I2 gives 2Hi. Second one. H2 gas plus I2 gas gives rise to 2Hi gas. Right? For this, I can write Kc as Kc is equal to, okay, Kc is equal to product concentration, Hi concentration square by H2 concentration into I2 concentration. Right? How can I get Kp? Because all are gases, partial pressure of Hi square by partial pressure of H2 into partial pressure of I2. This is how we write. If I write units, so concentration, moles per liter, okay, delta N we write. What is delta N? Here 2, here 1, here 1, right? So 2 minus 2, that is equal to 1. Anything, right? 2 minus 2 is equal to 0. Moles per liter power 0 is equal to 1. No units. In the same way, atmosphere power 0. Kp units. These are Kc units. That is equal to 1. Next reaction let us take. What is that next reaction? PCl5 gives rise to PCl3 plus Cl2. PCl5 gaseous gives rise to PCl3 gaseous plus Cl2 gas. So what is delta N here? Delta N is equal to 1 plus 1, 2 minus 1, that is equal to 1. Number of moles of gaseous products are 2, PCl3 1 mole, Cl2 1 mole, and number of moles of gaseous reactant is 1, 2 minus 1, 1, right? How can you write Kc? Kc can be written as PCl3 concentration into Cl2 concentration by PCl5 concentration. So units of Kc can be written as moles per liter. Delta N is 1. So moles per liter. Kp, if I write partial pressure of Cl3, partial pressure of PCl3, right? PCl3 into partial pressure of Cl2 by partial pressure of PCl5. PCl5. That is equal to units, if I write units, Kp units atmosphere power 1. That is equal to atmospheres, right? In the same way, if you see N2 plus 3H2 gives rise to 2NH3. Fourth equation, if you see. Kc, how will you write NH3 concentration square by N2 concentration into H2 concentration power 3. And how will you write for Kp? Kp is equal to partial pressure of NH3 square by partial pressure of N2 into partial pressure of H2 power cube. Right? Here, if you write units of Kc, Kc units is equal to moles per liter. What will be delta N? Delta N is equal to, what did you get here? 2 moles, 3, 1. Okay. Is that 1? 1. So delta N is equal to 2 minus 4, that is equal to minus 2. So you write minus 2. Then what I get, right? Liter per mole square. So liter square per mole square. Kp units is equal to atmosphere minus 2. That is equal to 1 by atmosphere square. Okay. So if you write for fifth reaction, this fifth reaction, so what will be Kc? This is solid, so we don't write that. NH3 concentration into H2S concentration by NH4 and HS. So as this is solid, it will be unit 1. Okay. So how will you write Kp? Kp is equal to partial pressure of NH3 into partial pressure of H2S. So what is delta N here? Delta N, these two are gases. So 2 minus 0, that is equal to 2. So what are the units of Kc? Moles per liter 2. That is mole square per liter square. What will the units of Kp? Atmosphere square. Okay. So that is how we represent Kp, Kc, and those are the units to write Kp and Kc. Okay. That is all with this session. In this session, we have discussed about law of mass action, how the law of mass action is applied for a reversible reaction. What is meant by equilibrium constant? When equilibrium constant is expressed in concentration terms, then that is called as Kc. If the equilibrium constant is expressed in partial pressure terms, then that is called as Kp. Okay. So let us wind up this session, and we shall meet again in the next class with another topic. Right? Thank you for watching.